All right, welcome everybody to the conference on Schrödinger's cosmic cat. I hope you've all seen the poster where we try to create a picture involving Schrödinger's cat, of course, but also Geneva and some sort of cosmic sense of superposition. Then I'm not sure whether artificial intelligence is sufficiently far advanced to convey all of that fully, but that was our intent. It's going to be a first conference in a number of conferences taking place in the context of a project funded by the Swiss National Science Foundation, which is why this sign is up here. It's a project concerned with the philosophy of beyond standard physics. So we're looking at attempts going beyond the standard model of particle physics and beyond general relativity. And of course, physicists are probing the physics beyond that in various directions, some of which we're trying to analyze from a sort of philosophical perspective. And we have three sub-projects, each of which has one person in main charge of it. The three people are Charlotte, Marta, and Niels, who are each in charge of one of the sub-projects. And the theme of this year's conference is going to be on the first sub-project, in which Charlotte works on her PhD, about how and in what sense the measurement problem of quantum physics may be relevant in cosmology, what we may learn from cosmology for the measurement problem or from the measurement problem for cosmology, and how we should even think of that problem, whether there is such a problem, of course, in that context. So I welcome all of you warmly here to this conference, two-day conference. I should maybe very briefly say something about the practical aspects. We will go for lunch, those of you who want to join us, to the university Mensa, and we do have coupons, right? So the speakers and organizers should be getting coupons. Everybody else is free to join us, but we cannot cover your expenses. It's not too much, it's of the order of 10 francs for a menu, which by Geneva standards is really very inexpensive. So that's for lunch. For dinner, we'll tell you more later. I propose we just get going with the first talk, which will be by Charlotte Zito on the cosmological measurement problem. Please, Charlotte.
Thank you, Chris, and thank you everybody for being here. I'm very excited for this event. So yeah, let's get started. So let's start with a very well-known story. So the story of quantum mechanics, a very successful theory with so many practical applications, never proved wrong experimentally, and yet plagued by the measurement problem in its own foundations. So why the measurement problem? At the very core of quantum mechanics, we find states like superposition states that have been referred to in the literature as quantum weirdness. And they sure seem weird if compared to what our classical reality looks like. There's not only superposition, there are also things like entanglement states, non-locality, and so on and so forth. So all these things really look weird if compared to what we are normally used to. But the thing is that we cannot get rid of them. So rather the contrary, they are really important for the functionings of quantum mechanics, and they are part of the reason of why quantum mechanics is so successful. But the point is that we are missing a sort of explanation. So the measurement problem kind of wants to deal about finding a proper explanation for why, first of all, we never see, we never experience superposition states or quantum weirdness, despite the fact that quantum mechanics actually predicts macroscopic superpositions, for instance. So quantum weirdness is not something that should be like relegated to the microscopic realm, but should really like also be part of our macroscopic experience. And that's a problem because we never actually observe states like this one. So it's an issue about explanation, but not every sort of explanation will do. We want to explain why we never observe quantum weirdness without referring to unanalyzable primitives such as measurement, observable, or consciousness. Now, why the cosmic cat? So why we talk about the cosmological measurement problem? So why does the measurement problem enter the cosmological framework? Well, this is another story. So the story of how like we have the standard model of cosmology, which is based on the laws of GR, which perfectly work on the to describe the largest scale structure of the universe. And they describe how the space-time geometry is related to the matter content of the universe and how they are related to one another, how they dynamically evolve. But the problem is that this description of space-time geometry based on the laws of GR breaks down in the early universe. And why? Because like in the early universe, we find that quantum effects become like more and more dominant at higher energies. And the point is that at a certain point, not only we have like quantum behavior and so on and so forth, the problem is that when we reach the quantum gravity scales, so when we reach the Planck scales, also the space-time structure starts like not to be there anymore, or at least not in the classical sense we are used to. So given that in the early universe we make use of quantum theory and quantum concepts and so on and so forth, the measurement problem is going to appear also there. And therefore we need to, well, first of all, address it and then possibly solve it. So that's why we talk about Schrödinger's cosmic cat. Now, the point is that once we realize that the measurement problem enters the cosmological framework, two immediate questions arise. So the first one is, okay, so we have the measurement problem also in cosmology, so not only in quantum mechanics and for what matters, I mean, every quantum theory. But how is the measurement problem in cosmology to be formulated? Because arguably the cosmological context, it's not really the same with respect to non-relativistic quantum mechanics, where we can do like experiments in our laboratories and so on and so forth. So cosmology is a peculiar science, so has its own methodology and so on and so forth. And arguably all these things are going to be different with how we treat the measurement problem in non-relativistic quantum mechanics. The second question is, okay, let's suppose that we find a nice way, a clear way to formulate the measurement problem in cosmology. How are we going to solve that? Because arguably the challenges that we find in the cosmological context might actually be different from what we are used to for the case of non-relativistic quantum mechanics. So the first question is a question about how we formulate the problem, so it's a question about formulation, and the second question regards its solution. Okay, now before going on, just a brief roadmap of the whole talk. So we have already started with introducing the cosmological measurement problem, and we have seen that these two issues arise in this context. Now, how are we going to start? So, okay, what are the things we can do to help us understanding, okay, how should I think about the measurement problem in cosmology? How am I going to formulate it in this peculiar context? And what I would like to propose is to use this idea of ontological clarity. Ontological clarity meaning being clear about what the fundamental structures of our theories, so of our models based on theories of quantum gravity, which have been applied to the early universe, so what these models are about. So the idea is to take ontological clarity as a sort of heuristic, so a sort of guiding principle to understand, like, okay, we have these models, what are these models about? And how am I going to address the issues that these models present within the cosmological context? Now, in this talk, so the cosmological model I will be referring to is loop quantum cosmology, and being loop quantum cosmology, sort of derivation of loop quantum gravity. We are going to see how this ideal of ontological clarity can be applied in the case of loop quantum gravity and then loop quantum cosmology, and see what sort of conclusions can we derive from the two models. And my thesis, it's going to be that the fate of spacetime in the early universe is part and parcel of the cosmological measurement problem. So we cannot hope to solve the cosmological measurement problem without also addressing, like, what happens to spacetime in the early universe. So without addressing the issue about the fate of spacetime. Yeah, so this is like, so this talk really focuses on the question about formulating the measurement problem in cosmology. I will say something also about, like, some hints about, some concerning about how it can be solved, but this is going to be like the very last part. Okay, so before going on, like, okay. So let's start with so addressing the question about how the measurement problem in cosmology should be formulated. Now, someone might say, okay, just look how the measurement problem has been formulated in quantum mechanics. We know that in quantum mechanics, usually it's formulated in terms of a trilemma. So we have, like, these three incompatible statements. So the first one regards, like, the completeness of the wave function, the second, the linearity of the Schrödinger equation, and then the issue about, like, determinate outcomes. Now, in quantum mechanics, the usual strategy, it's like, okay, since these statements are incompatible between one another, we just give up to one of them, and we obtain the different interpretations of quantum mechanics that have been put forward in the literature. Now, the question is, can we, like, maybe sort of translate the way the measurement problem has been formulated in quantum mechanics in the cosmological context? And I think that some problems emerge if we try to pursue this strategy. Because, okay, we have the early universe cosmology, and in cosmology, its main subject is the universe. But how are we going to think about a universal wave function? I mean, there are cosmological models based on this idea, but it's not really shared among everybody. So maybe we can do that, but there's some discussion that we need to do before, like, do this sort of translation. The second problem is that arguably in the early universe cosmology, we will not have a Schrödinger-like evolution. So that also needs to be discussed and addressed. And, well, these are just a couple of suggestions. There might be other problems. For instance, in non-relativistic quantum mechanics, it's fairly, like, it's easy to distinguish, for instance, observer and observed system. Might not be the case that is also doable within the early universe cosmology due to the physics that it's applied in the early times of the universe. Okay, so one can say, okay, just give up to this, like, kind of literal translation and just say, look, the measurement problem is the problem of explaining the emergence of classicality. So we are just going to do the same in cosmology. And that might be done, but the problem is that if we want to formulate the measurement problem in this way, which is, I think, the right way, we really need to be clear about what, the emergence of what we need to explain. So this means that we have to ask about the nature of the degrees of freedom that kind of leave the state of quantum weirdness and become classical. So this means that, again, we should be guided by this idea of ontological clarity about the fundamental structure of the cosmological models that describe the early universe. So I was inspired by this quote on this idea of ontological clarity. So Goldstein and Teufel, they write, conceptual problems of canonical quantum gravity vanish if we insist upon formulating our cosmological theories in such a manner that it is reasonably clear what they are about. Now, I'm not going to argue that all the problems vanish if we insist on the ontological clarity, but still, it's a useful heuristic principle that could be used. Great. And once we are clear about the fundamental ontology, we can maybe evaluate the different proposals for solving the measurement problem in the cosmological context. So first, we should be clear on what is there. So what degrees of freedom are we talking about? What are their features, and so on and so forth. And then we can say, okay, look, we have the different quantum mechanics interpretations. Which one is the more apt to address the issues that come up in this peculiar context? So let's start to apply this idea of ontological clarity in the context of loop quantum gravity, and for now I'm just considering the canonical formulation. So as you might already know, at the fundamental structures of loop quantum gravity are graph of spin networks. So spin networks are this graph made of links and nodes. They are the result of the quantization procedure that started with Hamiltonian GR. And one of the biggest success of the program of loop quantum gravity is that people have found a way to define the area and volume operators. In particular, the area operators, they gain contributions from the links, and the volume operators from the nodes of the spin networks. And the important thing is that these area and volume operators are discrete quantities. And so this has been one of the main results of loop quantum gravity. And one might say, okay, so we have these spin networks, what are they? And for sure, they are not entities out there in reality because, well, they are the product of the quantization procedure applied to spacetime itself. So it's not that they live on yet another physical manifold. So they should not really be thought as entities out there. How really should we think about that? It's not really easy to answer this question. Sure, they can be thought as the atoms of space-time, but they are not to be understood in the mereological sense that they compose space-time as, I don't know, bricks make up houses. And furthermore, there are lots of issues that actually come up when one tries to interpret spin networks. Well, first of all, spin networks are always in superposition. There is the issue about non-locality and the so-called disordered locality that has been discussed in the literature. So the fact that, for instance, the nodes of the spin network map to distant spatiotemporal regions in the emerging spacetime. As already mentioned, the theory is background independent. And well, there are all sorts of other issues coming from the Hamiltonian constraint and the empirical incoherence. So the lesson that has to be learned is that, be it as it may, space-time is lost in the fundamental structures of loop quantum gravity. And so one of the main issues for the quantum gravity program is actually to recover relativistic space-time some way or another. Now, at this point, one might ask, okay, so quantum gravity models, we do not have space-time as we know it. Space-time's gone missing. Do we need space-time for formulating the measurement problem? Is an indispensable ingredient, or maybe we can do without it? And so there's an argument that has been put forward by Haley, and so let's delve into that. So Haley starts by, so he has this sort of, so his reasoning starts with one premise about quantum mechanics. So in quantum mechanics, as I've already said, it's fairly easy to distinguish between the measurement apparatus and the observed system. One reason why we are able to distinguish between them is that they are spatiotemporally located. So you can say, okay, here is the measurement apparatus, here is the observed system. There might be other reasons why, but this might be one. And Haley says, okay, look, but in loop quantum gravity, the fundamental structures actually lack spatiotemporal connotations. And therefore, it's not the case that we can really model a measurement interaction in loop quantum gravity, because if we do not have space-time there, it's really difficult to maybe assign what is like a measurement apparatus and what's an observed system. And he claims that since we are not able to distinguish between environment and observed system in the fundamental structures of loop quantum gravity, there's going to be a limiting procedure in which these entities will emerge. And he actually claims the same about space-time. So he says that our familiar space-time structure will emerge in a suitable limit of the theory. So the way I interpret it is that we need space-time to emerge in a sort of limiting procedure to being able to distinguish between environment and observed system. Without it, we cannot do it. And therefore, he says, okay, a resolution to the measurement problem is not indeed a prerequisite for the recovery of space-time in quantum gravity. Therefore, the measurement problem is orthogonal to the problem of space-time emergence. So there are two separate issues, and space-time is going to be recovered by a limiting procedure. Now, there's already been sort of debate about the role of the limiting procedure in the literature. So the claim is that limiting procedures cannot really suppress interference, or so it's not even given that this is going to work. But this is not what I'm going to focus. So what I would like to understand is really if the measurement problem is really indeed orthogonal to the problem of space-time emergence. And for doing that, I would propose to move to the cosmological framework, so to loop quantum cosmology, and see what comes up there. Now, so this is based on loop quantum cosmological model in the FLRW universe so flat universe with lambda also equal 0. Now, loop quantum cosmology is an effective theory, and so one of the main claims put forward in the literature is that loop quantum cosmology describes a quantum geometry. A quantum geometry of the early times. And the important thing is to understand, okay, why do people talk about this quantum geometry? Well, the starting point of loop quantum cosmology is the kinematics of loop quantum gravity. And importantly, they assume the discrete spectrum of the area operator, which is called like the minimal length, which is transferred to the domain of loop quantum cosmology, so in the cosmological context. And then they put in the model some symmetries, as it is usually done in cosmology, so homogeneity and isotropy. And now I'm going like very fast, I'm skipping lots of details, but the result of all this is that in loop quantum cosmology, we are actually able to formulate the Hamiltonian constraint with both the gravitational and the matter content parts. So the way the Hamiltonian constraint is usually interpreted in loop quantum cosmology is that, so you have like nu, that describes like the volume of the universe, and phi, which is assumed as like internal time, and it's a scalar field. So here we are describing how the volume of the universe evolves with respect to this internal time, which is assumed as like cosmic time. And the important thing is that, like in the equation, there are some terms, some lambda terms, which derive from the discreteness of the spectrum of the area operator. So the thing here is that this lambda cannot really go to 0. So we cannot like calculate the limit for lambda going to 0 because it has like a minimal length. And this is relevant also for instance, singularity issues. And the relevant thing here is that this equation is actually a difference equation, exactly because there is a minimum non-zero eigenvalue of the area operator linked to this lambda term, which again cannot be squeezed into 0 but has like a minimal length. And then we have like these quantum bounces, so the universe bounces back, kind of helps solving the singularity issues. And the point is that in all these equations, if we look at the Dirac observable, so really the quantity we are interested in, the quantity to which we can attach like a real like physical interpretation is the volume, so which indeed describes the volume of the universe. So I really think that there is much more important like physical interpretation that can be attached to the way the Hamiltonian constraint is built in the context of loop quantum cosmology, and loop quantum cosmology somehow makes things easier to interpret with respect to the context of loop quantum gravity, where we have like all sorts of issues coming up. I mean, of course, in the cosmological context, we have, I mean, for instance, we have like symmetries. We only have like 1 degree of freedom. It's an effective theory, and so on and so forth. So there are all these issues that one should consider and evaluate eventually. But yeah, the important thing is that we have the volume of the universe that grows with respect to internal time. And to that we can attach a physical interpretation, which might be useful to understand like what the measurement problem is about, because then we can indeed interpret it as a quantum geometry that evolves and that becomes determinate at later times and higher energies. And this, I guess, is, I mean, we can interpret it as the problem of spacetime emergence. So there are the degrees that leave the quantum weirdness to become classical are exactly the degrees that concern the volume of the universe, so this quantum geometry. And that's why I think that in cosmology, the measurement problem has to take into account the fate of spacetime in the early universe and eventually explain why, from the quantum geometry, we obtain a classical and smooth and four-dimensional relativistic spacetime. Now, of course, all of this is conditional upon the use of the area operator from loop quantum gravity to loop quantum cosmology. There is some discussion in the literature about that. So, yeah, this is for sure something that needs to be discussed. And if this step is not granted, it might be that then we cannot take the volume as the Dirac observable, and then other problems might come up. So now that we have understood, okay, so like the basic ontology of cosmological models really can be thought as a quantum geometry with a physical interpretation. We can start asking, okay, so how do we address this issue? So how can we explain the space-time emergence in the early universe? What are the desiderata that we might want to put in we might want to have in our solutions? Well, first of all, some words about how we treat observers. So cosmology is about the universe, and we cannot assume like something external to it. So for sure, observers must be modeled within the system and must be relational. So arguably we cannot like use like an absolute observer that somehow explains how the quantum geometry becomes classical. The second issue is, okay, what kinds of mechanism can be used to explain the emergence of classicality? There are some in the quantum mechanics literature, but it's not granted that the same mechanisms that we used in non-relativistic quantum mechanics will work in the cosmological framework. Or maybe they can work, but they kind of need to be modified to address the issues about space-time that arise in the early universe. So one problem that I didn't really address is, okay, so how should we treat time? Because in the quantum gravity context, in the loop quantum gravity context, like the dynamics is less explicit than Schrödinger equation. So arguably we will need to do something else. We cannot rely on like an external time parameter along which the system evolves. So this must be addressed. And maybe one way to go is like, okay, we can use decoherence as it has been used in quantum mechanics, but decoherence is also a process that happens through time. So maybe we can use it, but we will need to adapt it, if possible, in cases where the time evolution is not Schrödinger-like. And then, well, of course, another desiderata is that the mechanisms that we use to explain the measurement problem need to be extendable to GR, because arguably if the quantum geometry is becoming classical and so on and so forth, it's becoming a GR geometry. So these mechanisms must be extendable to that. So yeah, that was all I wanted to say. Thank you.
All right, the floor is open. David.
Thank you. I wanted to worry a little bit about ontological clarity as a starting point. And my worry is something like this. In the non-quantum gravitational measurement problem, then if we look at different solutions to the measurement problem, they disagree radically ontologically. So if I have something like the Copenhagen interpretation, whose ontology as far as that one is classical, where the quantum formalism is doing something else, or similarly sort of neo-Copenhagen pragmatist type approach, where again the quantum formalism isn't doing ontological work at all. And then I compare to something like a hidden variable theory, where the ontology is generally taken to be primarily the hidden variables and the wave functions largely fulfill the guidance role. And I look at something like Everett, where the ontology is a sort of structure that's reading the patterns encoded in the wave function. And those look radically different. And so I worry that if we have as a strategy that we achieve ontological clarity prior to exploring solutions to the measurement problem, we're in some danger of sort of baking in our own preferences into the setup of the problem prior to trying to solve it.
True. Yeah, I thought about that. So one worry is that if you don't address like the issue about how do we interpret the fundamental structures of these models, and we kind of use the already existing interpretations of quantum mechanics to solve the measurement problem. This might actually raise other issues because maybe you use an interpretation which already has its ontology, and maybe the ontology of that interpretation heavily relies on the existence of spacetime. And then if we try to implement that strategy in a context that is not spatiotemporal, so my worry is that we are kind of forcing to interpret like spatiotemporally something which is maybe not that maybe does not have like all the, because when we define space-time like in GR, we want to attach it certain characteristics like or even how like space-time is treated in like non-relativistic quantum mechanics. Like we have this external parameter along with the system evolve, so arguably we are able, I don't know, maybe to measure distances, to calculate time intervals, and maybe if you have an interpretation of quantum mechanics that solves the measurement problem and that relies on these things, maybe not explicitly, maybe it's something hidden in the interpretation, and then you switch to the cosmological context, so to models based on quantum gravity theories where you maybe are not able to calculate distances and measure intervals and so on and so forth. Yeah, you're kind of forcing something that it's not there.
So that seems an excellent reason not to just take existing solutions to measure the problem uncritically and assume that they can be applied in the cosmological context. That seems absolutely right. But it doesn't follow from that it's safe to take the ontological clarity. Because again, my concern is if we tried this move in other places, we'd get the question. If we decided, for instance, that as an example where this is done deliberately, intentionally, take the kind of Rutgers primitive ontology style approach, which is absolutely saying we need ontological clarity. What we mean by that is we need to clarify the nature of the theory as described in space and time. Now, it would be unfair to say that begs the question in favour of certain solutions. It's done totally intentionally. They have a particular, I think, wrong or intelligently justified view as to why theories should work like that. But the point is the move is extremely non-innocent. It essentially commits to certain sort of strategy to solve the measurement problem. And again, my worry is that one tries to get ontological clarity prior to solving the measurement problem in this context. One is essentially going to bake in certain assumptions about how one thinks the measurement problem should be solved.
Yeah, I understand. Yeah, my reason for taking ontological clarity, was mainly like a tool to evaluate which interpretation. But
and that's it to see the forces pushing in that direction.
Yeah.
I want to face that as a worry about.
Francesca, is this a finger?
It's a failure, yes, because it builds on what David is asking. It seems to me that, so when we talk about solving the measurement problem in cosmology and in the absence of space-time structures, what you mean here is not specific of quantum gravity. It's just what happens with general relativity, where you don't have a preferred time, where you don't have a preferred relation, and so on. So what we are really addressing here is whether there is an interpretation of quantum mechanics in which the measurement problems still make sense, even if we are in a background independent theory, in a classical background independent theory. So in a certain sense, you're right. larger context when you go beyond just quantum mechanics.
Yeah, I totally agree. Sure, and of course, I mean, the loop quantum gravity program starts from GR, and GR is already background independent, so we already have features of the theory that already appear there. So, yeah, I agree with what you just said.
We have a lot of things there, and that's a finger as well?
Yeah.
Okay.
Let me see if I can put the phrase and tell you where I'm rephrasing incorrectly. And let me add something to it. The question about ontological clarity, or the question about ontology, as far as I understand it, is the question of what your theory is telling us that exists out there, and out there is space-time. That's normally what we mean by an ontology, right? This theory tells us that in space-time these local variables and so forth. And of course, lacking space-time and looking at the problem of emergence of space-time, it seems to me that you will not be looking to do it with such an ontology, which presumes the existence of space-time to give, to even pose the question, let alone give the answer. So is what you are proposing some type of bootstrapping scheme in which your ontology will become clear at the same time that your space-time emergence will become clear, and therefore somehow neither of them can be said to come first? Is that something of that?
No.
Would that be characterization what you're looking for, or am I missing that?
So, yes, usually we think about objects being located in space-time, so that's how, that's how philosophers usually think about the ontology of the world, so what populates our world. In theories where we do not have space-time, I think it's a fair question to still ask, to still inquire about the ontology of the theory, even if we lack space-time, or even if we lack aspects of space-time that maybe are very relevant, like in the, I don't know, emergent level, or that maybe we assume to be relevant for, in our classical reality, and that might not be there at the fundamental level of, for instance, theories of quantum gravity. But I mean, it's not going to be easy to interpret like what certain approaches to quantum gravity are really about, because again, the entities are not to be conceived as entities out there. It's not that space-time is, I mean, in a sense, it is built from spin networks, but not in a mereological sense. It's not that you are putting spin networks together and then you recover space-time in the same way you build a house. So for sure, you have to put some, I don't know, constraints on your ontology, and it's not going to be maybe trivial or straightforward. But still, if you do not, so my worry is that if you do not inquire about the ontology, you are just like simply giving up, even to understanding like which mechanisms can help us to recover classicality. I mean, if, for instance, Haley proposed Haley said, okay, space-time will emerge in an appropriate limit. And is the limit really the strategy we are using to recover the emergence of space-time? Is this really what we need to have emergent space-time? Or are there maybe other strategies that might be employed that are maybe, I don't know, that add explanatory value to our theory? So I don't think that we will reach ontological clarity once space-time will emerge from the fundamental structures of quantum gravity theories.
Words, that's very tricky.
Yeah, but just about David's question, just to see if I understand things correctly. So you can maybe distinguish between two problems, like the measurement problem on one hand, like if there's a collapse and it But then also, what is the nature of the wave function in quantum mechanics? So it's an ontological question. I would have thought to solve these problems hang together, right? So you probably have to solve them together. Be clear about ontology.
Like, what's the sequence here? I mean, as I understood Charlotte's position, then ontological clarity was something we had to achieve in advance prior to looking at wave function. So it would be slightly separate requirement to insist on ontological clarity as part of a solution to the measurement problem. And that could be tested, but if you did, people would argue that that's something one wants in a solution. But of course, that might mean different ontologies in different solutions.
In other words, you don't want to commit to a certain particular type of ontology, anything goes, but...
That was the concern. Charlotte is right as well. There's a certain amount of start problems.
Yeah.
Emily.
Thank you. I was wondering if you could say something more about your response to the Lee argument. So, as I understood it, the Lee argument was saying something like anything that we would call a measurement will take place in a regime in which space-time has already emerged, and that's why these problems are separate. The emergence must be prior to the measurement problem. And I don't think I fully understood what about the LQG example was supposed to refute that argument. So I wonder if you could clarify that connection.
Oh, right. No, I was not. Okay, here it is. So not in the. I mean, in loop quantum gravity scenario. So I'm a little skeptical about the fact that we cannot model measurement interactions in loop quantum gravity, that this is absolutely something we cannot do. Maybe we just need to implement like some sort of relational interpretation. But that was not actually my point. My point was like, okay, maybe let's be charitable, maybe he's right about the case of loop quantum gravity. Let's see whether this is also the case in the cosmological setting.
I don't quite understand what about so you're disagreeing with me, right? You're saying the measurement problem is not orthogonal to the problem of space-time emergence? I don't quite understand why you're saying that.
Because if the Dirac observable, so if what we have at the fundamental level, according to a certain interpretation in the loop quantum cosmology case, is exactly the volume of the universe to which we can really attach like a physical interpretation, and then it's like this quantum geometry that becomes classical at later times. I take this to be the problem of space-time emergence. So when you want to explain why this quantum geometry becomes determinate, you are indeed addressing the problem of space-time emergence and the measurement problem.
I mean, that seems quite consistent with what he uses, though, because what you seem to be doing there is solving the problem of space-time emergence without describing any measurements, really. And there's a further problem about what would then happen if you put something that looks like a measurement into that picture.
Yeah, but I'm like, there is some discussion in the literature about the role of limiting procedures. So I'm not sure that space-time really can emerge with this limiting procedure.
Right.
That was my, yeah.
But regardless of whether it can or can't, that is one problem. Then what he seems to be saying is that that's a distinct problem from the measurement problem.
Yeah, but then what's the measurement problem about? You know, that was my, I mean, if you have like space-time emergence and you have some way to explain it, and then the measurement problem is going to be about something else, arguably, so not about space-time. And okay, maybe, I mean, in like the early universe, there's like a hot, dense soup of like particles moving, and the measurement problem is only going to be like concerning these properties or these elements. That's what.
Okay, I have 3 fingers and I'll close the queue with that.
point in the sense that, like, I see what, I mean, if the measurement problem is defined as the problem of the emergence of classicality, I mean, I see why it enters in the debate of spacetime emergence, in the sense that, like, if you want to recover the classical spacetime, in a sense, you need to also address this problem insofar as, you know, it's an emergence of it's an example of an emergence of classicality. And then I guess, like, my question is, like, how this is different from any other example of emergence of classicality? Like, why this should be a special case? Like, why spatial emergence should be any different from, you know, how the measurement problem applies in other contexts in which you have, like, this issue of emergence of classicality? And my guess would be, close to what Francesca was saying, because, like, I mean, we're a bit outside of the, you know, domain in which we use to apply quantum mechanics. But then, like, if you want to go down this route, it's route like you end up saying, like, I mean, the problem are related, but the orthogonal, insofar as, like, you know, solving the measurement problem is not going to give you complete solution on the problem of spatial emergence, because there are other stuff and other problems going on there, like taking the continuum limit and so on. And, like, you know, solving spacetime emergence, or, like, giving some sort of boundary to the spacetime emergence is not providing a solution to the measurement problem, because, of course, like, you have the measurement problem in all the other contexts. So, I mean, like, how, again, I think, like, this position is not unreasonable. They're not completely, maybe they're not completely orthogonal, but for sure, like, they, it doesn't seem like one is, you know, necessary for the other.
Yeah, but so again, one thing is really, like, to find an accountable explanation of how and why spacetime emerges. And if you're not going to do that with the limiting procedure, you need to find another way. And I get it that, like, we have maybe problems about background independence also in other scenarios. But that's different with respect to non-relational quantum mechanics. I mean, there you assume, like, a classical background that's already there. And here you really have to explain space-time emergence with tools which are not going to, I mean, maybe they are the same for non-relational quantum mechanics, who knows, but there are some issues that need to be addressed. And they might be, I don't know. I mean, if we take the measurement problem and space-time emergence to be like two separate problems, yeah, then the main thing I think you are going to find a different explanation, different mechanisms for recovering space-time in the classical.
Francesca, briefly.
Yeah, I just wanted to understand better what you mean by emergence, because so here in this argument you need special temporal properties to define quantum mechanics, but some of them are already present in the quantum theory, like localization, like relational evolution, and so on. So it's really a matter of clarifying what you need more when we talk about emergence. Because if it is just, for instance, continuity, that is where you may have ambiguities and so on, then you can do quantum mechanics even in a discontinuous setting, like on a lattice and so on. But this is not the problem that we are discussing here about the emergent problem and so on.
Yeah, so the idea is simply so that with the emergence of spacetime, we want to recover some features of spacetime as we know it, and that are lacking at the fundamental level. Now, since at the fundamental level, like spacetime has become like quantum, arguably we might want to use like some mechanisms to explain like how this quantum becomes classical, because that's how our observations of the universe have worked so far. But yeah, so emergence, it's kind of used as a, like, in a general sense. So there are some features that you have to recover, and yeah, they actually should be like further specified, like to exactly understand, okay, I need this feature, I need to recover this feature, and then you can evaluate the different mechanisms. I don't know.
Sure. I mean, just quickly on your exchange with Emily, I take it what's going on here. He thinks that the measurement problem concerns measurement, and so if you can't define measurement, you can't have measurement problem. Your definition of the measurement problem makes measurement a bit of a misnomer, and the measurement problem is about emergent classicality. I like that definition. Healy will not like that definition, because for Healy, the quantum classical transition is not a dynamical process. And I think one thing that brings up is that it's, if you want to be any more specific about the measurement problem's definition than how do we make sense of quantum theory, it's mess, then it's harder than it looks to separate stating the problem from solving the problem.
Yeah, you're right. I didn't want to use the term measurement in defining like the measurement problem. Maybe that's where like me and him really come apart. So if we consider like, yeah, I mean, if he really needs the term measurement to be there, I'd rather not use the term, because it's, I mean, to me it's an analyzable primitive, and maybe we should rephrase it in other terms, maybe using like interactions or other sort of.
But notice that you beg the question there against people who think measurement isn't an primitive. It's quite hard to have a neutral statement.
Yeah.
I know that there are several more people who would like to ask questions and have fingers on this, but please ask her not to do it at the coffee break, and join me again in thanking her.